If you've never been to CppCon before, from year one, this conference has been designed to be a festival for C++. Other groups, they go to their keynotes, they just disperse. These people all day long are buzzing, talking to each other, learning from each other. And it's that vibe and that community that's really good.
All right, hey everyone. Welcome to my talk. Today I'm talking about the pattern matching that we already have. Now, there are some C++ pattern matching proposals. Has anyone heard of Herb Sutter's P2392 or Michael Park's P2688? Has anyone heard of these proposals? Okay, it's a few people, fair number of people. So I'm just going to show a little bit about, just one example from these proposals. So this example is adapted from Michael Park's proposal here. We create a shape that has a virtual destructor, and then we create a circle that inherits from that shape, and then a rectangle that also inherits from that shape. And what we want to do is we want to calculate the area. And so to do that, well, with P2392, we can use the inspect keyword. The inspect keyword is a prefix. It takes the argument shape, and then we're able to polymorphically deconstruct as a circle, we can deconstruct that into the radius, or as a rectangle, we can deconstruct that into the width and height, and then we properly calculate what the area is based on these two things. So this is handling polymorphism. With P2688, the syntax is, I would say, fairly similar in this particular case, but this case has match as an infix keyword. But similarly, we deconstruct a circle or we deconstruct a rectangle, and then we're able to calculate the area polymorphically. Now, I do not have a crystal ball, despite what you may see on the screen right here, and I don't know if these are going to get into the language at any point. The C++26 ship has sailed a few months ago, and these are not in C++26. So that means that there is no pattern matching in the language, right? There is. So the title of this talk is called The Pattern Matching We Already Have. So let's get into it. I have a function here. It's called foo. It takes a bool and it returns a bool. I have a function template here that takes a t, that is a floating point type, and it streams it to cout. And then I have a function that takes a unique pointer, and if that unique pointer has something, return it, otherwise return 0. These are three functions. They're all named foo. What happens if I call foo of a decayed lambda? What happens if I call foo of 123? What happens if I call foo of ABC in quotes? None of these types actually have overloads in the foo overload set, and yet all of these call code. These all actually compile properly. Now, to give the answer, they all call foo of bool. But really, the interesting thing is why. I want to know why. Here's another example. We create a struct template called isSame, and it takes a t and it takes a u, and it sets a value to always be equal to false. And then I create another template that is also called isSame, but now this time it's isSame of t comma t. And what that means is it has to be the same type, and now the value is true. So then I can static assert isSame int comma int, not isSame int comma int star. How does the compiler know? How does the compiler know which one of these things to match? What are the actual rules that take us through these things? I would call this pattern matching. In fact, I would call 4 different topics that I'm about to talk about pattern matching. We have function overload resolution, template specializations, template argument deduction, and class template argument deduction. And these are the things that are in the language today that almost all of us have the ability to use if you're in C++17. And I want to dive into the rules of how this kind of stuff works. So for this talk, I want to understand the basic mechanism of these facilities. I want to develop some analog reasoning about your code and, to give some insight into the logical reasoning of C++. This talk will just be scratching the surface. The minute details will be glossed over, and in 1 or 2 places, I will have some newly invented syntax for demonstration purposes. That's just how it goes. And please, I will take questions at any time. I am Canadian. I'm a licensed professional engineer. I like twisty puzzles. If you like these kind of things, come talk to me later. I actually brought a few with me to the conference. I've been working in C++ for a little bit over 4 years now professionally. I've been on the standards committee since 2023, and I run the Winnipeg C++ developers meetup in Winnipeg, Canada. If you're ever around there, please let me know, and I would love to have you at my meetup. Let's get into it. Function overload resolution. So, it's been in the standard since the beginning. It's in the C++98 standard, which, by the way, the draft is actually from before 1998, meaning that this draft that I was reading is from before I was born. It's a defining feature, excuse me. It's a defining feature of C++ compared to C. It is the example of pattern matching that I'm going to show that is not strictly just templates. And so I created this to show, look what they need to mimic a fraction of our power. In this case, if I want to create these two init overloads, how do you do it in C++? Well, you create your two init overloads. But if you want to do it in C, it's actually possible in this particular case. And I did it here. I adapted it from a Reddit post that I found. But it's not pretty. I mean, you have to define init that then uses init inside of itself so that it can only expand once, of course. If you want to do anything more complicated, you might have a chance in C++. You might not, in C. You might not have a chance in C. In C++, it's really easy. And it is one of the big defining features, I would say, of C++ compared to C. One of the other ones, of course, being destructors, but that's not what this talk is about. So I'll talk about some examples of function overloading. This will be interactive. And then I'll talk about how overload resolution works. OK, I have these two declarations here. I have f of int, like the regular lowercase int, and I have f of capital int, where capital int is an alias to int. Now, are these two declarations redeclaring the same function? Hands up. Okay. Are they two separate overloads? Hands up. Okay. Or is this ill-formed code? Like, is this a compile error? Hands up. Okay. So it turns out this is actually redeclaration. So how aliases work in C++ is an alias is just another name for exactly the same type. And so if I create a function that, if I declare a function with one type and then with an alias to that same type, it's just the same function. So capital int means lowercase int. That's what aliases are. What about this case? I have an enum that has int as an underlying type. I have f of int and I have f of e. Are these two functions redeclaring the same function? Hands up. Okay, it's a couple. Are these two separate overloads? Hands up. Okay, it's a lot of people. Or is this ill-formed code? Is this just a compile error? Okay, so yeah, these are two separate overloads. In C++, an enum is a distinct type from the type that is its underlying. So you are allowed to have these two functions, and they are two separate functions, even though in this case you can actually create an e implicitly from an int. This is actually from the C++98 standard itself. It's an over.load. If I have f of int and I have f of const int, are these two functions redeclaring the same function? Hands up. Okay, are they two separate overloads? Hands up. Or is this ill-formed code? Hands up. All right, this is a redeclaration. It doesn't look like it, but it actually is. And that's because in function parameters in C++, we actually drop the top-level const. So this is f of int. Both of these are f of int. They're declaring the same function. What about this case? F of int star and f of const int star. I'm not saying the proper type because that actually may give it away. Are these redeclaring the same function? Hands up. Okay, are these two separate overloads? Hands up. Or is this ill-formed? Hands up. Okay, so they are two separate overloads. As I said before, we drop the top-level const. This is not a top-level const. These are both mutable pointers to their respective types. So the first one is a pointer to int. The second one is a pointer to const int, but they are both non-const pointers. And so these are two separate overloads. This is also from the C++98 standard. Are these three functions? Actually, I should say what they are. We have f of char star. We have f of char array that is unbounded, or f of char array that is bounded with an extent of 7. Are these three separate declarations redeclaring the same function? Hands up. Okay, are they three separate overloads? Hands up. Or is this entirely ill-formed code? Hands up. Okay, the room is a little bit more mixed on this one. These are redeclarations. And that's because, similarly to how a top-level const qualifier just gets dropped in a function parameter, an array actually turns into a pointer. So in this case, all three of these things are just f of char star. And this might be why you see int main sometimes written as the argv might be char star star, it might be char array array, it might be char star array. All of these things are valid because the actual function signature is just the double pointer, right? All arrays get turned into pointers in function parameters. This one is a little bit more complicated, not quite interactive. I have two overloads here. This first overload has three declarations to it. The first one is declaring it the first time. The second one is adding a default value to j. And the third one is adding a default value to I. Okay? So it's a function that takes two arguments. Now I have a function that takes no arguments. And it's also called f. Okay? And this is completely allowed. So when I call f of 1, 2, well, that calls the first overload, of course, because the first overload is the only one that can take two arguments. If I call f of 1, this also works because the first overload is the only one that can take two arguments, right? Or the only one that can take one argument, I'm sorry. It will turn into two arguments once it's actually called. This will actually call f of 1, 99. What about calling f with no arguments? What happens? Well, it's an error, because the compiler doesn't know whether you meant to say f with two arguments where both are defaulted, or f with no arguments actually for real. So this is a compile error. There are ways of disambiguating, but I'm not getting into that in this talk. So, sorry? Ah, okay, nice calling that out. On line 4, excuse me. On line 4, we are missing a default for j. We are not, because that's on line 3. So you can only declare a default value for a function one time. If you ever declare a default value for your parameter, if you declare it in the header, you actually cannot also have that in the body, right? You may have, or sorry, if you declare it in the header, you can't also have that in the source file, right? And people may have run into this before. You might have int j equals 99. You cannot also have int j equals 99 in your source file. You can only declare a default value one time. So it's already there. It's on line 3. And actually, that's a good point, because when I was writing this talk, this is something that really, I found this really interesting. I didn't know you could do this, and you can do this. This is valid code. Yes? If you would swap line 3 and 4, does it still compile? Ah, good point. Yes. If you swap lines 3 and 4, this will not compile. Because on line 3, it sees a declaration where you are giving a default value to the first parameter without giving a default value to the second parameter, and that will not compile. So yes, that is a good point. Thank you all for pointing that out. I should have mentioned that before. So yes, that is exactly right. Okay, back to being interactive. If we have a struct and then we have two functions, they're both called f, and they both take no arguments. One's static and one's not static. Redeclaration, hands up. Overload, hands up. Ill-formed code, hands up. Okay, yeah, it's ill-formed code. You can't have a function with the same name, the same parameters, where one's static and one's not static. What about this case? I have void g and void g const. Redeclaration, hands up. Okay, two separate overloads, hands up. Cool. And ill-formed, heads up. So these are two separate overloads. And you may have written something like this before. If you want to overload your functions such that you call one of them when x is when you have an object of type const x versus when you have an object of type non-const x, this is how you overload between them. What about void g and void g ref? Are these redeclarations? Hands up. Okay, two separate overloads, hands up. Or ill-formed code, hands up. Okay, this is ill-formed code. And the reason this is ill-formed code is because these are actually shadowing each other. So the one with the L value reference is actually shadowing the one without the L value reference, because the other one also takes an L value reference. And you just can't write a function. You can't declare a function twice inside of a struct or a class. And then last interactive example here, all of these 8 functions, this is the famous octuplication, it's overloads. So these are 8 separate overloads. You can write this if you want to, and I apparently did. So cool. I want to talk about the general mechanism of how function overload resolution works. I'll talk about the context of overload resolution, how we grab the possible candidate functions. From there, we grab the list of viable candidate functions, and from the viable list, we have to find the best candidate function. Okay, there are 7 distinct contexts of overload resolution. I will actually name them as 5 because in the standard, 3 of them are kind of indistinguishable to an average developer, which I definitely am. So there are function calls, like when you have an identifier and you have parentheses after that, like foo. There's object operator parens, like when you have parentheses after an object, operator parens. There's operator overloading, like if you have 2 strings and you do a plus b, where a and b are both strings, you have overloaded the operator plus, and so that's a different context. You have constructors, which is another context, and then there are 3 contexts that have to do with conversion functions, and I won't go into the details of those right here. So depending on this context, you grab your set of viable functions differently, obviously, because with function calls, they will be your functions named whatever. With your object operator parens, it will be those, etc. So those are the contexts. These are named in the standard. Once we have those, we grab the list of viable candidate functions. So we grab all the candidate functions from the context. We grab the list of arguments. Then we remove the candidates that have the wrong number of parameters. We remove the candidates that have unsatisfied constraints. And then we remove candidates that have incompatible arguments. Now, I'll go over a big example of this here. So here I have 8 possible overloads where one of them is templated. This one has a default value. This one has an ellipsis parameter, a C variadic. And this one is a template function, a function template, where it requires that the size of t is equal to 3. And then I actually want to call foo of nullputter. And obviously nullputter t is none of these options. And the question is, which of these does it call? It calls one of them. It's not ambiguous. So let's start with our set and let's whittle it down. So first of all, we are trying to call foo with 1 argument. Which of these cannot take 1 argument? Well, it's 1 and 4. And that's because 1 can only take 0 arguments, and 4 can only take 2 arguments. All of the other ones could conceivably take 1 argument if you give it a sufficient argument. Now, we get rid of the function templates that have unsatisfied constraints. So this one has an unsatisfied constraint because nullputter is not 3 on any architecture that I've ever heard of. So this will always be eliminated from the set. And then finally, we remove these 2 candidates, number 2 and 3, because nullputter does not convert to double and it does not convert to int. So we're left with these 3 overloads, where nullputter actually would be valid if each one of these 3 was the only overload. So now we have to grab the best candidate function. I'll briefly mention implicit conversion sequences. We grab the implicit conversion sequence for each parameter argument pair. The implicit conversion sequence is something that is mentioned in the standard as the sequence of steps that it takes to get from your argument to your parameter, how you convert from one to the other. In fact, there was a really good lightning talk on that at CPP North a few months ago, so you should watch that once it's online. Then we rank the viable candidates based on the conversions. And so these are the 3 candidates that we have left. For the first one, this is called a nullputter t to variadic. It's an ellipsis conversion sequence. That's what it's called in the standard. It's an ellipsis conversion sequence. The second one is a standard conversion sequence because it deals with 2 types that are built into the language, 2 fundamental types. And then we have a user-defined conversion sequence for the last one. Now, I made this simple by not creating more than 1 function of each type because there is actually a ranking between these 3 types. So a standard conversion sequence is the highest ranked, followed by a user-defined conversion sequence where you've defined the constructor yourself in code or in the standard library, technically. And an ellipsis conversion sequence is ranked lowest, so the variadic will rarely get hit. So it calls foo of bool. Cool. In a lot of cases where you're not sure which function overload it's calling, if there is a bool overload, it often is that one. Just kind of interesting how that works. So yeah, that's all for function overload resolution. For now, I'm just scratching the surface, as I said. Potentially maybe another talk in the future if people want to hear this kind of thing. But the details go very deep, and I want to talk about template specializations. These have been in the standard since the beginning as well in the C++98 standard. They facilitate the type traits in C++11. And there is a header in the C++98 standard, matching, it says matching, of class template partial specializations. And that's some vindication for me, because when I start writing this talk, I think, well, is this really pattern matching, or am I just seeing things? No, it is pattern matching. So one could imagine some syntax, maybe based on one of the pattern matching proposals for future C++ versions, where you might want to match 2 types using the match keyword. And if those 2 types are the same, return true, else return false. This is not real syntax. Demonstration purposes only. If you put this into your compiler, it will not run. Maybe you have some extension that you've written yourself, but then you're just trying to prove me wrong. So you have a primary template here. If you want to actually write this in C++, you can write this, where you have a primary template. This is in C++ 98 code. And then you have your partial specialization that has a match criterion that is saying the argument t must be the same. And when that's the case, it will match either one or the other. If you want to turn this into C++ 11 syntax, we can write exactly the same thing. It's a bit simpler. We have our static context per bool and our other static context per bool. And again, we have this match criterion here saying that we can only have one type. The type has to be the same. And when that criterion is satisfied, then this is the body of the class that we use, else we default to the primary template. So even though we don't have that nice pattern matching type syntax, we have other pattern matching syntax that, yeah, maybe isn't so nice, but it definitely gets the job done, and it's very robust. It also powers the type traits. So we have this trait called remove const in the standard. This is just one that I'm giving as an example. And inside of it, we have an alias called type that we set to be equal to t. And then we have our partial specialization that matches const t. That's our match criterion here. So if we match a type that has a const on it, we just remove that const. We just drop the const. And then the alias is the type without the const. And in that way, it just removes const from any type that we give to it. If we give it a type that does not have a top-level const, then it removes nothing. So template specializations, how does it work? In broad strokes, we have primary templates, partial specializations, and explicit specializations. And I'll go into what each one of these are. Now, quickly, out of a show of hands, who here has written an explicit template specialization? That's more people than I thought. Who here has written an explicit template specialization in production code? That is the same number of people. Very shocking. Okay, nice. I would love to know about your use cases later. I have actually never written these in production code. I've written them for fun. So a primary template looks like this. I'm just showing off the anatomy here. So we have the template head, which is the template keyword followed by the parameters. And then we have struct or class or a function, but I'm just talking about classes. And we name it, and then we have our brace. Nothing in between, and then we have the body. This is very different from the syntax of a partial specialization, where we, yes, have the template head, of course, but then when we name our struct, we have to follow that with some template arguments. So basically, I like to imagine it as we are taking the template parameters from this template that we have just written, and we are passing it back into the primary template. Conceptually, that's how I visualize it. And if you notice, there are two template parameters in this template here, and yet we're passing them back in as one template argument into my trait, right? Because the primary only had one template parameter, and so we need to make sure they have the same number. So this is a partial specialization. It still has a template head. And an explicit specialization also has a template head, meaning it has the template keyword. However, the difference is that it's empty. It has no arguments, or no parameters, I'm sorry. And then when we actually define the struct my trait, well, we have to give it all of its arguments as concrete types, or at least concrete from the perspective of where we are. And then the body, again, can be the same. It can be entirely bespoke. And I'm going to show that off here. Here I have a primary template, an explicit specialization, and then a partial specialization. And if you notice, the bodies actually have nothing to do with each other. They are completely unrelated. And that's one of the cool things about template specializations. You can create bodies that have nothing to do with each other, meaning you can conjure up some really wacky things. Typically, you probably shouldn't be doing that if you want other people to read and maintain your code, but I'm just exploring what's possible, and I want to show off, you have to know what not to do in order to know what to do. I want to show off something in the standard. There is a famous passage. Has anyone here seen this before? Few people. When writing a specialization, be careful about its location, or to make it compile will be such a trial as to kindle its self-immolation. It's a limerick. People call this the limerick, if people have heard of it in the standard. It's still in the standard to this day. This is actually the stable name of where it's at in the standard today. And it basically means if you are writing partial specializations and explicit specializations for your types, if you put them in the wrong order, your code's maybe not going to do what you thought it was going to do, so just be careful. That's basically what it's saying. If you don't exactly know what you're doing, you probably shouldn't be writing explicit specializations. And I say that as someone who has not written explicit specializations in production code, because I may just get it wrong. And also, there's something called explicit instantiations that I'm not even getting into right here, which is something that I always confuse for explicit specializations. That is a completely different thing. So anyway, maybe another time in another talk. So I want to talk about specialization matching. So you use the explicit specialization if it's available. It is a concrete type. It is not a template. Even though it has a template head, it is not a template. And that's because the number of parameters in the template is empty. So it's not a template. So you use it if it's available. Otherwise, you use template argument deduction, which I will talk about in the next section, to match the partial specializations. If there are no matching partial specializations, you use the primary template. If there's one, you use it. And if there are matching partial specialization, if there are multiple matching partial specializations, you choose the best one. Okay, what does that mean? Let's get into an example. Here I have struct A. I have defined my primary template here. It takes in two template parameters, T1 and T2. Then I have my struct A that is a partial specialization here, another template. And this is matching when the first parameter, or the first argument, is a pointer type. And then this partial specialization is matching when the first parameter, first argument, is a pointer type. Getting it wrong. When the second argument is a pointer type. Okay. So just on intuition, if I instantiate A of int comma int, is it 1, hands up? Is it 2, hands up? Or is it 3, hands up? Cool, that's a really good intuition. Because yeah, I mean, you see this here, and int comma int, neither of those are pointers, so it's not gonna match either of the ones that are partial specializations on when one of the types is a pointer. So it's 1. What about A of int star comma int? Is it 1, hands up? Is it 2, hands up? Or is it 3, hands up? Okay, so yeah, this is 2, and you just see like the form, it's just the same, right? Like this case, you can look at this intuitively, and you see int star comma int. Well, T1 can get matched as int, and T2 can get matched as int, and there we are with number 2, the partial specialization on line 2. Right. As I said, if a partial specialization is matching, then we use it. Are we matching 1, the default case here, the fall through? Okay. Are we matching 2? Or are we matching 3? Okay, no one said 3. We're matching 2. And that's because pointer to pointer to int, pointer to pointer to pointer to int, is still a pointer. And so it will still match as being a pointer type. And so this is 2. What about A of int comma int star? Is it 1, the default? Okay, does it match 2? Or does it match 3? Okay, I think that was everyone here got 3. And yeah, I mean, it's the same form, right? So it matches 3. Here's the complicated case. We have A of int star comma int star. Does it match the default fall through case? Does it match 2? Or does it match 3? Okay, so yeah, a few people had their hands up for both 2 and 3, because yeah, it matches 2 and 3. Which one is it?
Well, it's ambiguous.
It's ambiguous. So let's get into how this matching actually happens, and then we'll disambiguate later. We actually rewrite the class templates as if they were function templates, and then we use template argument deduction later and overload resolution to actually determine which of these partial specializations we use. But it is specified in the standard in terms of template argument deduction. So whatever template argument deduction does, that's what we do here. So I'll use a more intuitive, hand-wavy kind of thing in this section until we get to the next section. And ultimately, we use the specialization that corresponds to the resolved function. So here are the templates again. Now, we rewrite the partial specializations as if they were function templates. So I'm going to write these imaginary functions here. These aren't real functions. As per the C++ standard, you are not allowed to define a function with this name because it has a double underscore, so that's why I wrote it like this. So number 2 gets rewritten to this. Now, conceptually, this is how we think of it, right? We have this imaginary function that takes whatever our template is, so it's A of T1 star comma T2, and it has the same template head as the partial specialization on line 2, and then we have a similar thing for line 3. So now that we have that, we can throw away the original example, and all we're doing is actually, we're doing some intuitive template argument deduction here. Just what we can do in our heads. Okay, so if we call imaginary function with an A of int star comma int, it calls 2. And that's because as a function template, the reason why it matches 2 is because as a function template, it is able to match against imaginary function that I labeled 2, and it is not able to match against the imaginary function that I labeled 3. in terms of template argument deduction, right? And you just look at it, the forms just don't match up, right? So, kind of intuitive like I did it before. And if we call imaginary function with a of int comma int star, then, similar thing. But if we call imaginary function of a with a of int star comma int star, the problem is it's ambiguous because both of them match, but as per function overload resolution, there actually is neither candidate is better than the other candidate, and so it's completely ambiguous, right? Could be 2, could be 3, therefore it's neither. So let's add a number 4, and this will actually disambiguate. So if we add a 4 that matches for when the first type and the second type are both pointers, well, now it's not ambiguous anymore. So we have this new imaginary function here that is, almost the same as the others. It corresponds similarly to the one that the partial specialization on line 4. And now, if I try calling imaginary function of a with a of int star comma int star, well, it could be 2 and it could be 3, but actually 4 is a tiebreaker because it is further specialized than 2 and 3. So I won't get into the nitty-gritty details of what all of that means right now. I'm just sort of trying to build an intuition here. I would love to get into template argument deduction. But if anyone has any questions about the previous sections, I would love to answer right now.
On slide 53,
On slide 53,
it looks like the comments don't agree with each other.
why?
You have int and then int star int.
Yeah.
Int star, and then the lower ones have int stars in the brackets.
I'm sorry, can you repeat that comment?
Where it says calls 2, calls 3 in the other
Yep.
2 lines, there's commented sections in the angle brackets
Yeah.
indicating what should tie to T1 and T2.
Yes. Okay, I see what you mean. Are you saying that the imaginary function, how did I do this? So are you saying that this highlighted one has the template parameters in the wrong order?
Well, I wasn't sure. It shouldn't be int in the angle brackets.
No, because it would be matching against the partial specialization on line 2, or like the one that I've labeled 2. So it's matching for a T1 star, but it's matching for a T2. So with T1, the actual type that it ends up being, we drop off the pointer. So it ends up being int for the first template argument, but it's int star for the second template argument because we don't match against a pointer type, we match just against any type. And actually, that question perfectly leads into the next section, believe it or not. So we'll be talking about template argument deduction. And we'll actually be going through the steps of how to go through template argument deduction like in an analog way manually. I think it's really cool. It's my favorite part of the talk. Maybe I'm the speaker, I shouldn't say that. So let's say we have a function template called foo that takes a stood vector of t. Has anyone here written a function that looks almost exactly like this? Okay, I should ask, has anyone here not written this function before? Yeah, right. I mean, yeah, it's like the most basic template function you'll ever write. If we create a stood vector of int, we can call this function foo with just foo of vec. Have you ever thought about why? Like, we don't call it with foo angle brackets int of vec, right? We can do that. We don't have to. And that's because of something called template argument deduction. So if you've never thought about this, I love this part. So it's since the beginning in the C++ 98 standard, we can deduce template arguments of the function template without actually specifying them as template arguments. And it makes a lot of C++ code, a lot of templated code, it makes it a lot easier to read. It makes it a lot easier to write. You don't have to remember to put the angle brackets, and then if you're in heavily templated contexts or nested template contexts, you need to put like the .template keyword if you want to specify. No, use template argument deduction. You never have to worry about that kind of stuff. You can specify some template arguments explicitly. It just complicates things. So oftentimes we just don't want to write the template arguments, and template argument deduction makes that really nice. We also have some new semantics in C++ 11 having to do with forwarding. Okay, I'll get into the general mechanism. I'll talk about non-deduced contexts, and then I will talk about forwarding. So the general mechanism for template argument deduction is that for each function parameter argument pair, so for each pair of function parameter and function argument, we ignore the top level const volatile qualifiers. We Oh, I was one behind. We process the parameters and the arguments special forms, which I'll get into on the next slide. And then we match the template parameters to the corresponding template arguments. And we'll do that step by step. So the special forms here are either an optionally const volatile t, a pointer to t, a reference to t, an r-value reference to t, an array of type t with an optional extent, a function that returns a t that has any number of parameters u with an optional no except, a pointer to member, a template with stuff in it, or a template with nothing in it. Now, this isn't exactly as it's specified in the standard. I'm just trying to make it a bit more readable for slide code. If you actually go into the standard, it shows it similarly, but not quite. So here's a function template. It takes in a t star. What I want to do is I want to call foo with the address of a stud vector of int. Let's go through the steps and see how we actually can match what t is going to be when we actually call foo. So we have to match up our parameter argument pairs. So our parameter is of type t pointer, or pointer to t. Our argument is of type stud vector of int pointer. I say star. So parameter t star, argument stud vector of int star, right? They both match the form t star. Therefore, t is a stud vector of int. And that's because we drop off the pointer part of it, and we just sort of recursively go in and we just match the parts that are down the line, right? So this seems pretty simple. Is this good for everyone here so far? Cool, let's get more complicated. We have a function that takes a stud vector of t star. And then again, we pass in exactly the same thing. We pass in the address of a stud vector of int into this foo. So our parameter is a stud vector of t star. Our argument is a stud vector of int star. Now, of course, intuitively, we as people look at this and say, well, yeah, t is int, right? But of course, also, we as programmers know that computers don't do anything intuitively. We have to spell out the steps explicitly. So again, we match this form t star. And because they both match the form t star, we can remove the pointer. So then we just have stud vector of t is stud vector of int. Okay, that's one level deeper. Now we have to go another level. We have to match another form. And the form that we have to match is a template with some t in it, where this template is known to be a stud vector. And so because the template is known to be stud vector, we can just peel that back. And we're left with t being int because we go down the line and match up the parameters with the arguments. Cool. So this one was a little bit more complicated, but hey, we just did template argument deduction manually, by hand. Did anyone think they were going to do that today? Kind of cool. I did. So we have this function template here, also called foo. Now it takes in a vec of t star. What is vec? Well, this is also a template parameter. It is a template parameter. So we're actually going to have to match on this one as well. But again, we pass in the same argument that we've been passing in before. We pass in a pointer to a stud vector of int. And again, we go down the line. The parameter is a vec of t star. The argument is a stud vector of int star. They both match the form t star, so we peel back the layer, we remove the pointer. Now we have vec of t is stud vector of int. So we match the form, they both match the same form, a template with some type in it. And because they both match this form, we go down the line and we match them up individually. So vec is stud vector, and t is int, right? Because we match up the template part of it, and then we match up each of the individual parameters inside the template parameter. So we have just done template argument deduction with a template parameter. Kind of cool. Was there a question here?
Yeah, I was just wondering about the ellipses. Do you need those ellipses for this example?
You're wondering about the ellipses. Do we need the ellipses for this example? No, I don't.
Okay, is there a reason to add them, just in case there's multiple arguments?
Yeah, so the reason to add the ellipses here, sorry? Right, yeah. So the reason to add the ellipses here is that the function template called stud vector actually has two template parameters.
That's right.
So if we only left in one, it wouldn't match. But if we put in two, then it may not match our own custom vector that only has one parameter. So I find, at least me specifically, when I am writing template parameters, I usually just do class ... just so that it'll match anything, even though when I'm actually writing my function parameter on the next line, I'm just calling vec of t with a single parameter. So, but yes, no, that is a very good question. Thank you.
I think it was fixed in 20.
I'm sorry?
I think it was fixed in 20. I think before 20 you needed it. After 20 I think you didn't.
Before 20 you needed the ellipses, but after 20 you don't need the ellipses to... Allocators are defaulted. Interesting. Okay, right. Even though it's default, I didn't know that. That's interesting. Yes?
This is super annoying when you have NTPs. And like class doesn't match.
Yeah, this is very annoying for non-type template parameters or constant template parameters. Yeah, it is very annoying because it's completely heterogeneous, where you would have class or auto or int or whatever. Like those are completely heterogeneous, very annoying to deal with. Reflection will take care of a lot of that, but I still want universal template parameters. Not part of the talk, but I want those. Was there a question back there? Yeah.
You say that vector has 2 template parameters?
Yes, vector has 2 template parameters.
Could you also get the second template parameters, like by having a comma, class comma t, class comma u? Or?
Yeah, you could get the second template parameter if you have class t, comma, class u. And then you would just take foo of vec of t, comma, u. And then in that case, it will still match std vector. It will actually even match std vector of int, even though you didn't specify the second template argument because it's defaulted. But it won't match anything that might be custom. And it also won't match anything that has 3 template parameters. So, it will match only exactly 2. I wrote it this way so that it's more general. It matches anything. So these are good questions. Thank you. Okay, this example is more complicated. We now have 2 function parameters. We've done 2 template parameters. Now we have 2 function parameters. So now I'm actually passing in a vector and a pair into my foo. And so we go down the line, we match against our parameter argument pairs. So we start with a parameter that is std vector and our argument is std vector of int. We match the form template of some type t, where this template is known to be a std vector, and therefore we deconstruct that, t is int. But we're not done. We have to go through every parameter argument pair. That's how template argument deduction works. So the parameter of std pair of t, comma u, the argument is a std pair of int, comma float. We match the form some template of 2 types, where this template is known to be a std pair. Therefore, we deconstruct that. We go down the line, t is int, u is float. Okay, does this look good to everyone? Okay, it's about to not look good to everyone. So now we have exactly the same function template, but now I'm calling this with a std vector of int and a std pair of double comma float. Any predictions on what's going to happen? I'm hearing murmurings of it won't compile. So we have our parameter that is a std vector of t and our argument is a std vector of int. Again, we go through the same steps that we've been going through. We match the form. Template is known to be a std vector, strip that off, and then t is int. Great. And then again, we do the same thing for the second parameter argument pair. The parameter is a std pair of t, comma u. The argument is a std pair of double comma float. Strip off the std pair because we know that it is the template that is there on both sides. So we match that t is double and u is float. Yes? So t is int based on the first parameter argument pair. T is double based on the second parameter argument pair. This does not compile. Or at least, this is a substitution failure. This may compile if you have another overload of foo. I'm not going to say it wouldn't compile if you don't have other code around, but if you have just this code, it will not compile. Here's an example from the standard, actually. This is in temp.over. You have a function called max. And max takes a t and then another t, and it just tries to determine the maximum, right? A lot of people will write code like this. I'll often write code like this and then wonder why it's not working. And you'll say, well, what do you mean not working, right? Because if I call max of 1, comma 2, well, this will return 2, and it'll compile, right? It'll deduce t as int. So this will call max of int with our function parameters int, comma int. And that's great. And max of 1.0, comma 2.0, well, this will also work, right? This will call max of double with our 2 function parameters double, comma double. What about max of 1, comma 2.0? Has anyone run into this before? Okay, I see a lot of head nodding. That's some good commiseration, thank you. So the compiler cannot generate this instantiation of this max function template. The reason being, how does it know what t is, right? Just in the previous example, like this is a lot simpler. We go down the line, we try to find out what our template argument is. We have int as a template argument. No, int is a function argument in the first position. And so that matches against t, so t is int. And then we have double as our function argument in the second position. So t is double. Well, is it int or double? How does the compiler know, right? And we can't just say that the compiler, oh, we just choose the leftmost one or we choose the rightmost one, because that would mean that if you swap the order of parameters, that might actually change which instantiation gets called, and that's not very good. So this is, also an error. There are ways to fix this though, and this is where I'm getting into the next subsection of non-deduced contexts. So this is a little bit of ugly code, yes?
If you call it explicitly with one type, will it compile?
Yes, it will. If you call it explicitly with one type, it will compile. And actually, at a previous job, that is what I did to clean up some of our code base. So yeah, you absolutely can do that. And that is where using the non-deduced template arguments actually might come in handy if you're in a situation like this, where you actually cannot necessarily provide the same two arguments, and you also can't change the definition of the function. So like std_max, for example. I think std_max is defined like this as well. It's even worse, it's references. So here, this max function actually now will work for heterogeneous types. The reason being that, well, the second parameter is some garbled mess of laundering the type, right? So this actually is still t. It is t, but the thing is, I'm passing it through this, I'll call it a laundering mechanism of std type identity. You don't have to use type identity, you can really use anything, but type identity is like, the canonical one for this. And because I'm passing it through here, now b is not deduced. So I can call max of 1, 2, I can call max of 1.0, 2.0. I call max of 1, 2.0 and it works. But of course, that's only if I have access to change the definition of the function. So this will call max of int. T is deduced to be int. And the reason here is the first function parameter function argument pair is the one that has a deduced context. The second one has a non-deduced context, so it just doesn't even participate. So that works. Hey, nice. So the non-deduced contexts, there are 10 cases of this in the standard. I will talk about 3 of them that might matter to most people. There is what's called a nested name specifier of a qualified type name. That's just what we saw, and I'll get more into that. There's a decal type expression, and then there's this weird case if your parameter is not a std initializer list, and yet the argument is a braced init list. I'm showing this one because it's really subtle, and I guarantee you that almost everyone in this room has run into this before. So reading it like this, you're like, I've never run into that. That's too complicated. You have, I promise. But we'll talk about the other non-deduced contexts first. So I have a struct template called s, and it has a type alias that is int. It is always int. And yet, when I have this function template foo, we cannot deduce t. Like, I would say, intuitively, the reason why we can't deduce t here is, what if there is another specialization of s somewhere else that defines an alias to be something else? The compiler can't rule out that fact, and so this is a non-deduced context. My standards members in the audience, does that sound about right intuitively? Yeah, okay. So let's go down the line. We have our parameter, which is a type name s of t : type. This is a qualified name. The nested name specifier of this is s of t. Nested name specifier is just a fancy way of saying everything to the left of the rightmost scope operator, the rightmost : okay? So that's our nested name specifier. It's a non-deduced context. Everything to the left of the rightmost : is a non-deduced context always. Most of the time, you don't have a template parameter in that nested name specifier, so it doesn't matter. But here, the template parameter is there, and so you can't deduce this, because that whole thing's a non-deduced context. And therefore, we just can't deduce t. Here's another example. This time I have the same struct template, but I have 2 function parameters. So we go down the line. Let's try calling foo of 123, 456. We go down the line. Again, the first one is exactly the same. We cannot deduce t because s of t is a non-deduced context. It's to the left of the rightmost scope operator. But we have another parameter argument pair. And so we have our parameter t and we have our argument int. So t is int, and we're fine. So in this case, it works, right? The non-deduced context is on a per parameter argument pair basis. Here's another case. We have our struct template S, and now we have foo that takes a decal type expression. Now, we know what this is going to be in all cases. And yet, as per the standard, this is a non-deduced context. We cannot deduce T if we try calling it with an S of double. T should be double here, intuitively. Yes?
Can you briefly go back to the slide where you had the type identity?
Type identity? Or is this one fine?
No, well, let's go back to type identity.
Okay, I'll go all the way back to type identity.
I noticed you didn't use the alias type identity T,
Yeah, I didn't use the alias type identity T.
because if you use that, then we wouldn't have anything to the left of the rightmost.
Exactly. If I use the template, if I use the alias type identity underscore T, then everything to the left of the rightmost double colon will not exactly make sense to my point. But you know, back to something I said in the beginning of the talk, an alias is just another name for a type. An alias is not itself a type. And so I actually have to dive into what is the type actually. So if I used std type identity underscore T, that is not the type. The type is std type identity underscore T colon colon type is the real type. Yeah, so, but exactly. I did this carefully, yes. Yeah, no, because I mean, it would have been confusing if I would have said, oh, well, to the left of the, yeah. So if you do run into that, all of your underscore T's in the standard library, like type identity underscore T or add const underscore T, those are all aliases. So in reality, they are like add const colon colon type. Okay, thank you for pointing that out. Okay, I will get back to where I was. So here, basically, I have this parameter, and it's a decal type expression, which is a non-deduced context. Therefore, we cannot deduce T. I've never tried this. This is just, you know, a case that some people here may have run into. And then here, in this non-deduced context, this is a non-deduced context. Now, we have a function template that takes a std vector of T, and we're trying to pass it a braced init list of 1, 2, 3. And this is something that I've tried a million times, right? And you cannot deduce T by this. And it's a very specific rule in the standard, and that's why I'm pointing it out. Our parameter is a std vector. The argument is a braced init list. Because our parameter is not an initializer list, but our argument is a braced init list, it causes a non-deduced context. So we are able to deduce T if our argument was something else. But because our argument is a braced init list, it won't work. So that's just something that I want to point out. It's a rule specified explicitly in the standard. And then I'll talk about forwarding briefly. It's a special mention in the deduction rules that says an R value reference to a CV unqualified template parameter, blah, blah, blah. It's a tref. That's all it is. It must be a template parameter of the function itself. It cannot be in any sort of enclosing template context. In the standard, it's referenced as it's mentioned as a Heisen reference. I think that's kind of funny. If I create an int and then I try calling f with that int, T actually deduces to be int ref. That's strange. And in fact, that was my impetus for writing this talk. I didn't quite understand why that was. So that happens. If I call f of 0, then T is deduced to be int. And that one actually makes a little bit more sense. And I'm surprised that I was confused by the L value case. I thought I would be confused by the R value case. So I'll briefly mention reference collapsing. If you take a reference to a reference to T, that's the same as a reference to T. If there is an L value reference anywhere in the chain of references, it collapses to an L value reference here as well. But if you have an R value reference of an R value reference, then it's an R value reference. Now, of course, this is not real C++ syntax, but this is real C++ syntax. So I have my reference to int, and then I take a reference to that alias. That's completely allowed. What is this R2? Well, it's reference collapsed. You have your reference to int. That is a reference to int, right? References are not like pointers. You can have a pointer to pointer to pointer to pointer. You cannot do that with references. So, and if you have an R value in the chain anywhere, so if you have an L value reference and then an R value reference to that L value reference, you are left with an L value reference. Similarly here, an L value reference to an R value reference is an L value reference, and then an R value reference to an R value reference is an R value reference. Okay. I'm saying the same thing a million times. Yeah, but that's just how this goes. And the reason why I need to talk about this is for the reason I'm about to, well, we'll go through the rules. So if I have an int and then I call foo of I, let's do template argument deduction on this manually. Our parameter is tref, our argument is int ref. We match the form tref. Huh? No, we don't. Well, we do though, because int ref is actually secretly int ref, right? We can add as many R-value references on top of that as we want, and that's idempotent. So, that's the word. Sorry, try to use big words. So therefore, tref is int ref, and we can just drop the outer ref, t is int ref. And there we are. So if t is int ref, therefore we call foo, where the template argument is int ref, and the parameter is int ref. Well, it's int ref, but again, that collapses down. Okay, so this is something that did not make sense to me until I actually worked it out line by line. Hopefully I can share that with everyone here. If there is one major takeaway, like one technical major takeaway to this talk, it is this is how forwarding works. So, I mean, simplified, but this is how forwarding works. Now, if I have the same thing, but I try calling foo of 0, it actually is a lot simpler. And I was surprised by that. I thought the R value case would be simpler than would be more complicated than the L value case. Not true. So our parameter is tref, our argument is int ref, match the form tref, t is int. Like it just works. Okay. And finally, I want to talk about class template argument deduction. I guess I'll have to speed through this. It's been in the standards since C++17. We call it CTAD. It's the same as template argument deduction, but shocker, for classes. And we say resolving a placeholder for a deduced class type. What is a placeholder? Std pair, p, passing it 1, 2.0. Std pair is not a type, it is a placeholder for a type. So here it deduces this as std pair of int, double. Likewise, if we have a function that returns a std vector of int, we can just say std vector v equals foo, right? Std vector is our placeholder, it deduces as std vector of int. I'll talk about the general mechanism and I'll talk about deduction guides very briefly. The general mechanism is that we create a theoretical set of functions that are called the guides. There's one for each constructor, one for each deduction guide. And then we do overload resolution and template argument deduction very similarly to template specializations. The winning function's return type is the one that's chosen. So again, I'm going to use the same syntax that I used before. So we have a struct template called myStruct. It has a concrete constructor and it has a template constructor. And so what we do is we create, again, an imaginary function that corresponds to the first constructor. And we create an imaginary function, it has the same template head, and then it has whatever the argument, or whatever the parameters are, and it returns a myStruct with the proper template arguments. And then here we have, this is the template head if you put both of the two template heads together, of the struct template and of the constructor template. And then again, it's a similar thing. This is the imaginary function. Now, if we create a myStruct with a vector, 1.0, a double, this is deduced as myStruct of int, double. This is just built in. You don't have to write anything special for this to work. And it uses the rules of template argument deduction that we have already talked about, so I won't go into that here anymore. If you call myStruct with an int and a std pair, it will now deduce this as myStruct of int, char. And this will actually use the second constructor, and it will use the imaginary function from the second constructor. Okay. Now what happens if I try passing in a vector and a pair? What does it do? Well, it actually matches the first imaginary function because it's more constrained than the second, right? The first is not a template, or it's not a constructor template, even though the whole struct is a template. But the constructor itself is not a template, so it matches the first one more readily than the second one, even though it matches both. But what if I wanted to make it ambiguous? Well, what I could do is add another parameter to the first, I could add a parameter to the first constructor, right? Std vector of t, a allocator. And now, right, it's changed. And now the imaginary function has also changed. And therefore, when I try calling this, it's ambiguous. How do you disambiguate? Deduction guides. Has anyone here not written deduction guides before? A few people, okay. So they give you specificity with how CTAD behaves. They are defined after a class template. They must align with the available constructors. So I'm just, squeezing it up. And here is a deduction guide. This deduction guide is saying, if we create a myStruct with no template, if we use myStruct as a placeholder, and we pass in a std vector and a std pair, this is how we will deduce it. And what it does effectively is it adds another imaginary function to the set. This is the new one. And so this imaginary function corresponds to that deduction guide. So the deduction guide, you can think of it as like forward declaring a constructor but there's no actual constructor that corresponds to it. It has to match up with a real constructor. And so now, when I call my struct with a vector and a pair, it will actually deduce this properly, and it will call the first constructor. Great, that's how you disambiguate. But you have to be careful. The return type of the deduction guide has to correspond to a constructor. You have to be careful with that. So if I change it to being this, if the deduction guide returns a mystruct of t comma u, then even though class template argument deduction itself may succeed, there will be no matches because once it succeeds class template argument deduction, there is no constructor for it to call. So this actually will fail. There are no matches. So that's the briefest introduction to class template argument deduction. In conclusion, C++ does actually have pattern matching. We have function overload resolution, template specializations, template argument deduction, and class template argument deduction. And basically, I read the standards so you don't have to. If you're interested, here are the sections that I read. It was quite a lot. CPP reference is also very helpful. And so I would say, listen, we already have pattern matching. The general rules can be quite elegant, but the edge cases are very gnarly. So I think we should reason in an analog way about our code. It's a muscle. We have to exercise that muscle. Let's get curious, and let's appreciate how far C++ has come. So thank you all so much. Yeah, I'll take questions maybe out in the... No, I guess, well, if the cameras are still rolling, then I can take a question. But I'll take one, sure.
All right, thanks. This is a great talk. It's going on the list of mandatory talks for our company for new people. I would encourage everybody at the YouTube space to kind of do the same. I think it sounds like a complicated topic, but this is something every programmer has to deal with. Yeah. And so this is awesome. I have a comment earlier on your examples with the const int and array. If we think of those as stood decay, then it might help us think about how those things actually interact, because that's where stood decay comes from.
Yep.
And on the argument deduction, they all happen independently, and then they're compared to make sure they're the same. Yes. I've run into people where they thought that the order was important.
Yeah.
So where do we go? Yeah, where do we, and the people watching on YouTube, where do we go for more information aside from having to grok the standard?
Yeah, that's a good question. I really like the Jason Turner method of just open up Compiler Explorer and try things. Because I mean, that's how I learned a lot of the C++ I know. Yeah, in terms of either written material or spoken material, I don't know. I don't have anything off the top of my head. But thank you. And yeah, I would agree that yeah, with the constant and with the arrays, that is where stood decay comes from. So I will just mention that explicitly. And yeah, thank you so much.